Okay, so today's lesson involves a topic called improper integrals. And an improper integral happens when you're trying to find the area of some kind of something that's inherently infinite. And I know it seems like how could you find the area of something that's infinite? But suspend your disbelief for a moment. Um, I, I want to have you look at two functions that I'm going to take a look at analytically in a second. First one is 1 over x squared. Now, I only really care. I'm only looking at the first quadrant right here, the positive side of this. So ignore the side on the left. If you look at 1 over x squared, there's two parts of it that can be infinite. You can see the integral, because there's a vertical asymptote at 0, the integral from 0 to 1 is infinite because, right, this thing never actually touches the y-axis. And then another integral that's infinite is the integral from 1 to infinity. And you can tell looking at this that from 0 to 1 looks a little wider here than from 1 to infinity. But this is going to happen in essentially any rational functions. We call these p functions, where you have x to some power and it's in the denominator. So if we think of a different one, 1 over the square root of x. So in this one, p value would be said to be 2. In this one, p value would be said to be a half. It's the opposite. See, now it looks very skinny. The integral from 0 to 1 of this function looks skinny, and the integral from 1 to infinity looks wider. And there is a necessary relationship between, if you change the p-value, if you make one of these sections wider, the other section gets narrower. And I want to show you how you evaluate it, because number one, at first thought, a lot of students don't even believe it can be evaluated, and I'm here to prove that it can be. But the other thing is there's a little ticky-tacky, tedious kind of notational thing in here that is important, because if you get asked this on an AP FRQ question and you don't write it in the right way, you're going to lose points. So let's say I'm asked to find the integral from 0 to 1 of 1 over square root of x dx. Okay, the way I have to solve this is by creating a new variable. I'm going to call it b, and it's called a dummy variable. And I'm going to rewrite this as limit as b goes to 0 from b to 1 of 1 over square root of x dx. And technically, you have to keep writing that limit as b goes to 0 of, what would this be? This would be 2x to the 1/2 evaluated from b to 1. And then that equals 2 square root 1 minus 2 square root b. And at this point, you can say that that equals 0, and you can say that this equals 2. And if I did the other side of it, the integral from 1 to infinity of 1 over the square root of x dx, again, I need a dummy variable. This time b is going to infinity. Which would be limit as b goes to infinity of 2x to the 1/2 evaluated from 1 to b, which would equal 2, so this would be 2b to the 1/2 minus 2. And you can think of this, and I guess technically you would want one more limit as b goes to infinity. And this is one where I'm not always as picky as other math teachers. This is, I think, if I understand what you're trying to communicate to me, then I feel bad taking points off, because I feel like that's the extent of what a language should be, is we should try to use this to understand what the other person's trying to communicate to us. But on the AP test and in other classes, you'll be penalized, I think, if you don't keep putting this limit as b goes to infinity. This part right here is 0. So this answer, or not 0, is infinity. So this answer is going to be undefined. So you notice with 1 over square root of x, we got one side that was defined and one side that was undefined. Now if I do it with the other one, 1 over x squared, you might close your eyes and make a prediction of what you think is going to happen. And just let's see how this plays out. This is going to be limit as b goes to 0 of the integral from b to 1 of 1 over x squared dx, which is equal to the limit as b goes to 0 of negative x to the negative 1 from b to 1. And this actually is a good trick that I remember discovering for myself after a couple of years of taking calculus, that when you're evaluating an integral like this and it's negative, it's the same thing as just flipping the boundaries. So I can just do b minus. This would be the same thing as limit as b goes to 0 of x to the negative 1 evaluated from 1 to b. So I just do that in my head and I get rid of the negative sign. And so this is going to be 1 over b minus 1. And this 1 over b part goes to infinity. So this is undefined or does not exist. And if I do the other side, the integral from 1 to infinity, I'm going to get the same thing, negative x to the negative 1 evaluated from 1 to b, which is limit as b goes to infinity of 1 minus 1 over b. And this part goes to 0, so this part equals 1. And in a normal year, I'd give you more time to practice around with these and figure out what the specific rule is with these p-series things like I was talking about before. But since it's not the normal year, I'll just tell you that there's always going to be, if the power is not 1, 1 is a rare, unique case that we'll talk about later, like the integral of 1 over x. But if it's 1 over x squared, 1 over x cubed, 1 over x to the 4th, the side that's going to, if this value, exponent right here, is greater than 1, the side that is going to converge is the side that converged in 1 over x squared case, which is the by the way, converging means it has a finite value. This from 1 to infinity will converge if this exponent is greater than 1. From 0 to 1 will diverge if this exponent is greater than 1. And that's the exact opposite of what will happen if this exponent is less than 1. So this is x to the 1/2. And from 0 to 1 will converge to a finite value. And from 1 to infinity will diverge to an infinite value. So that's undefined, or you can write diverges. This is an important topic because it blends into it guides us to the topic at the end of the year. But we'll get to that at the end of the year.